Professor Lambert has made many outstanding contributions to the understanding of string theory and M-theory, and currently holds a professor position in the Department of Mathematics, King's College London. In addition, from 2010 to 2013, he was a physicist at CERN, and his research is primarily concerned with supersymmetry, string theory, and M-theory. Today, Professor Lambert will be giving a talk titled From Higgs Boson to Superstrings, followed by a short Q&A. So, Professor, you can feel free to start.
Oh, well, thank you very much. It's a pleasure to be invited to this event. As always, it's a little bit peculiar these days to speak into a machine, but I'm getting used to it. So I'm happy to give this talk, which is a bit of like a mathematician's apology, but for string theory. So we're going to be talking about the Higgs boson, which of course was discovered 8 years ago now, after years of searching. And I'm going to try to use that and explain that to justify why it is a guy like me and my colleagues are interested in 11 dimensions. But for the most of the talk, I want to explain about the Higgs boson and some interesting things about it. Let's see. So I divide the talk into 3 sections, and it's inspired by this politician. I don't know if you remember him. It was in the days when we thought things couldn't get any worse. There was this guy called Donald Rumsfeld who invaded Iraq, famously, announcing that they were going to be welcomed with flowers. But he did say one clever thing. He thought that there were the known knowns, the known unknowns, and the unknown unknowns when talking about invasion. But I want to talk about physics and our understanding of the universe. And then I think we can divide it into the known knowns, the known unknowns, and the unknown unknowns. And so I will divide this talk in the same way. So the known knowns are what we know, what's experimentally verified. And for a particle physicist, that's what I'll be speaking about, it's the standard model of particle physics. So I'm going to spend the first third of the talk talking about the standard model of particle physics. And of course, in there is the Higgs boson as the last puzzle, the last piece of the puzzle to be discovered, more or less. Meaning that whatever comes next will not be in the standard model, although there are a few peripheral things to explore, mainly values of coupling constants. But there are mysteries associated to the standard model. It is the most successful scientific theory ever written down, in the sense of its scope about what it describes. It describes everything from deep inside a proton, the quarks, all the way up to macroscopic scales. And it only starts to break down, well, I wouldn't even call it break down, but in planetary scales, it's not really very useful. When gravity needs to be taken into account in black holes, it breaks down. So it's astonishing because it describes all these things and with no known error. It agrees with experiment every time it's supposed to. There are, of course, discrepancies, but that might not be because the theory is wrong, but because it's being misused or is not meant to apply. So it's astonishingly good. And it's been 50 years of research on it. It dates from like roughly 1970. Accelerators have been built and they found everything. Billions of dollars spent smashing things together, and every prediction of the standard model has stood up to tests. So that's an amazing achievement. And it is actually relatively simple, conceptually at least. But it leads to these questions. And so those are the known unknowns. There are things it doesn't do. It doesn't do quantum gravity. It has this hierarchy problem. And it has a cosmological constant problem and dark matter, which I will review. I imagine you're familiar with many of those words anyway, but I will review them. But those are the known unknowns. Those are the things we know where it fails, where it's not doing what we want it to do. It's not a failure of the theory, though, I would say, in the sense that it's a wrong prediction. It's just that the theory is not working for a number of reasons there. It may not be meant to work. But going even further, even with those things considered, the known unknowns, there are the unknown unknowns. These are the theoretical issues that we have when we think about particle physics. And these lead to things like grand unified theories, supersymmetry, and string theory. These are our guesses for what's going to come next in physics. And next, well, it's really more next to next. Next might be understanding dark matter. And then as we go higher up in energy, maybe we run into things like supersymmetry and string theory. Okay, so with that in mind, let's start with the known knowns. So this is the standard model of particle physics. So there are 4 known forces in nature. Gravity, which we all know, that's the one we're most familiar with. It's the one that's holding us down in our chair. I'm assuming you're all sitting down. It's certainly holding you onto the Earth. And it holds the planets in amongst the stars. Unfortunately, I don't seem to have a pointer that works. So I don't know, I'm scared to touch any buttons. So I'll just describe it. So there's gravity is an attractive force between all bodies in the universe. So it keeps, the apple falls on Newton's head, it keeps the moon around the Earth, and it keeps the Earth and planets around the sun, and the sun around the center of the galaxy, and the galaxies all orbit themselves, each other too. And we'll talk about it later. We have a lot of intuition about it, but I'll say one thing now is when it comes to particle physics, the atomic world, it's pretty much irrelevant because it's so tiny. It's only important because it's always additive. So on large scales, it's actually the only force because all the others cancel out. And that's why it's got the dominant role in the structure of the universe. The next most obvious one is electromagnetism. Here we already see the idea of unification. Because electromagnetism is electricity and magnetism. They were once thought to be different, but it was realized in the 19th century that they were combined, and in fact, famously by Maxwell. I'd like to call him a colleague at King's, but of course he was long dead before I got there. But he did do his famous work when he was at King's, in which he wrote down the laws of electromagnetism, which some of which had been found by other scientists, such as Faraday. So that's electricity and magnetism unified. And electricity and magnetism is a force, and it's mediated by exchange of light. And he realized that light is the fluctuations, the wave-like nature of the electromagnetic field. And that's the notion of unification. And of course, Newton was a unification too, the idea that the force of gravity is the same for the apple as for the moon and the sun. Well, we have to jump forward now to the 20th century, where the structure of the atom was realized. And you know that you have the Rutherford model, experimentally determined, that there's a dense core of positively charged protons and some neutrons as well, and then the electrons orbiting in somehow. Well, at first glance, that's okay, but second glance, you'd have to say to yourself, well, what in the world keeps all the protons together? Because they repel, they have positive electric charges, they should repel each other. Well, you don't do things very creatively, so there must be a stronger force, and that's called the strong force, and that's the one that's holding the protons close together, even though they electromagnetically would like to repel each other. So that's known as the strong force. And actually, in the modern language, it's replaced by something called QCD, which is quantum chromodynamics. And what that is we now know that the protons and neutrons are not fundamental particles. They are made up of constituent quarks. 3 quarks in each one, and the quarks are glued together with something called, yes, gluons, another fantastic name. And it's the gluons, well, they have a force called the color force. Well, why is it called the color force? Well, because you often just draw, they don't really have color, of course. You just like to label different quarks in different ways. So you color them in different colors on a picture. And then there's a force that sort of rotates the colors, and that's the chromodynamics. So that leads to quantum chromodynamics. It's the force between quarks, and which is mediated by gluons, and gluons are the analogs of electromagnetism, of the photons of the electromagnetic waves in electromagnetism. But that force is pretty much confined to be inside the nucleus of an atom. It doesn't even get outside the nucleus. It stays inside the protons and the neutrons and leads to this binding of them inside the nucleus. And the reason for that is something called confinement. And lastly, we have another force with a great name called the weak force. And the weak force, well, yes, atoms are strong and they bind together, but actually not always. Sometimes they just fall apart, right? There's beta decay or something like this. So there's something that is acting against the atom, if you like, but not very strongly, because by and large atoms are strong. So there's a weak force, a force that's weaker than electromagnetism and the strong force, and that leads to radioactive decay. And it's not all bad, because it's radioactive decay, or actually inverse radioactive decay, that powers the sun. That the sun is a great big nuclear reaction, which is undergoing inverse beta decay, and that's lighting up our world for us. So it's powering the sun, and therefore that's powering basically life on Earth as we know it. So those are the four forces. This is also, the weak force is also subnuclear. It doesn't extend beyond the nucleus of an atom under normal circumstances. But they all been encapsulated into this standard model of particle physics. So let's talk a bit about what the standard model of particle physics is. So it's a mathematical theory. It's very precise. And it describes all of these forces except gravity. Gravity is too weak to have any effect at the scales of atoms. So you could sort of include it in an effective way, and it wouldn't do anything. And we'll come back to what happens if you try to include it in a fundamental way later on. So the primary understanding is that the fundamental objects, matter, are made of point-like particles, particles which have no substructure. And also it's a local theory. What does local theory mean? It means that particle over here, particle over here, they don't interact unless they touch, unless they can really get together. So Newton was very worried about his force law of gravity, because it's called spooky action at a distance. The sun was acting on the Earth, reaching out through space, apparently miraculously, instantaneously pulling the Earth in. He was worried about that, as he should have been. That sounds unnatural. And we would worry about that, but we don't think that's the case. What's happening with particles is that they continuously emit the radiation quanta associated to, say, electromagnetism or the strong or weak forces. So there's a picture there on the left, which is an electron coming out, and that wavy line is a photon particle or a gluon that's being emitted. And it's emitted at one point, so it's all local. There's no reaching out over space. Now, how you have something like scattering, where you have two electrons that come in and then go out. Yes, the electrons themselves never touch. They repel before they get close. But what they do is they exchange one of these photons. And that photon reaches out across space at the speed of light and is absorbed by the other one. And the photon carries momentum. And that's how they exchange momentum and deflect each other. And if you don't believe me, you can get your friends together. You go outside and you stand on skateboards. Each friend stands on a skateboard. And you get a really heavy ball. You probably need a heavy one, like one of these medicine balls you use in gymnastics. And if you throw it between your friends standing on skateboards, you will repel. And that's this process. So the standard model is based on these ingredients, as well as another key ingredient, which is special relativity, which is Einstein's famous theory from 1905, that says that time and space can be rotated into each other. And that's actually a simplifying feature of the standard model. Relativity is a great organizing principle. It makes things simpler, actually. Perhaps if you're studying it, it doesn't seem like that. But it is a unifying principle inside the standard model. So it's a quantum theory, which also means that, by the way, there's a wave-particle duality. So it's rather neither here nor there if I think of an electron or a photon as a particle or actually as a wave. We'll come back to that later. So as I said, it was written down around 1970, which is to say it had a few corrections since then. They discovered more generations, but the basic idea was written down in about 1970, and it's been confirmed by experiment ever since, and really to an amazing accuracy. So here at the bottom, I've listed the famous anomalous magnetic moment of the electron. It's called G, or actually it's usually G/2 minus 1 is the anomaly, because basic relativity tells us that G equals 2, but then there are corrections due to these quantum effects. And there the corrections are written down, and you see the difference between theory and experiment, and PPT there means parts per trillion. Right? So they're off by a part per trillion, the difference between theory and experiment. So that is astonishingly the best calculations into theory ever experienced by the human consciousness, if you like. Right. I see. I don't know if there are any questions or anything at this stage. Should I pause? Well, let me just continue. So the Standard Model itself has 17 types of particles, and I've listed them there. The fermions, matter particles.
Interrupt for a second. There's some questions in the chat, so if you just at the bottom of the screen click in the chat, there's questions that if you feel like answering, they're there for you.
If I stop sharing, which is probably a bad idea. I can see the screen.
Okay.
Well, what's the particle that mediates the weak force? That's the W or Z bosons. It's the name. And the particle that was exchanged is indeed a virtual photon. The ones that are exchanged are called virtual photons. What is the physical meaning of path integral convex continuity? Let's postpone that for the questions later. Does the electroweak combination come into this? Yeah, it'll come up a bit. EPR, let's postpone that for after the question.
Yeah, so if you prefer, we can just take a list of the questions and then at the end we can put them to you.
Yeah, I don't know. All these talks are all slightly different. I don't mind stopping every little bit just to see, but some of them can be answered quickly and some deferred.
Yeah.
But let's leave them then, because I think it's going to be easier. So I'm going to go back to sharing my screen. Oops. And every program is different, so use Teams a lot. Okay, so here is the standard model. So it's got these 17 particles. They're the quarks, up, down, charm, strange, top, bottom, another great list of names. And then there are associated leptons, of which the electron is the most famous, and the neutrino the second most famous. But actually, everything comes in one of the oddities of the standard model is it comes with 3 copies of all these things. So there's the up quark, down quark, electron, and neutrino. That's called one family. But then there's another family, charm, strange, muon, neutrino, and a third family, top, bottom, tau, and tau neutrino. And they are mathematically copies of each other. All the differences, the only difference is their masses that get bigger and bigger as you go from left to right. So the lightest ones are up, down, electron, neutrino. And then you've got the force-carrying particles, the gauge bosons. So these are the quanta, of course, this is the electromagnetic field or the weak force. And so with electromagnetic field, you have the photon, it's the quantum of the electromagnetic field. For the gluons, which are the quanta of the chromodynamic force, the gluons are the QCD force. And then you have the W's and Z's, which are the bosons associated to the weak force. They carry the weak force in their quanta of a weak force field that permeates everything. And then, of course, the star of the show is the Higgs boson, which I haven't yet got to. So that's interesting. It's interesting in a way. It's why there are 3 generations is a huge question. They are complete copies, more or less, of each other. But you and I, as far as I know anything else, is only made of the first generation. We're all made of up quarks, down quarks, electrons, and we have neutrinos shooting around us. The rest is, exists for a fleeting moment inside some accelerator. But that's still great progress, because if you compare that with the periodic table, which I've written down there, the periodic table has like 100 elements with random properties. We've only got 17, and actually many of the properties are fixed. So it's a huge achievement, it's a huge simplification. And of course, you can explain the periodic table from relatively elementary considerations in quantum mechanics, based on just having a proton and an electron. Okay, so it's a great thing, and just to show it to you, there it is. So that is the so-called Lagrangian of the standard model. So it's there to impress you, as is the picture of me standing next to Atlas. That's like, I always say that's my calling card. If you get a talk like this, and the person who's giving you the talk doesn't have a picture of themselves next to a particle detector, then they're a fraud. So That's me next to a particle detector. Of course, I have nothing to do with experiment in string theory, but I've gone near it. But there's the Lagrangian. So if you know classical mechanics, you might know Lagrangians. And if you have a Lagrangian, that defines a mechanical system for you. Well, the same is true in quantum field theory. If you get a Lagrangian, you can use that to define a quantum field theory. And that's the Lagrangian for the standard model. It's slightly messy. It takes a page, but you could also say it's amazing because that's the one page. That explains every single experiment we've ever done, with the exception of ones involving, high scale gravity, which we haven't actually done any experiments. So that explains everything. And it fits on one page. And actually, conceptually, it's not that bad. Conceptually, you can write it like this. It's got a sum of various things. There's a sum over the forces, F mu nu. If you're familiar with electromagnetism, that's the Faraday tensor, the F mu nu that you see in Maxwell's equations. But there's an F mu nu for electromagnetism, and then there's an F mu nu for the weak force and an F mu nu for strong force, QC. And then there's the sum over the matter fields. That's the sum over the quarks, neutrinos, and electrons. They're all fermions. They're described by spinors. That's the psi that's written there. Those forms are fairly fixed. There's actually no ambiguity in what they look like. Symmetries fix what those terms are. The next line is this famous Higgs, which we're going to come to. And in fact, most of the stuff on this screen is the coupling to the Higgs everywhere. That's the most complicated part of this story. And it's actually the last line. So the middle line is the Higgs, and that's actually fairly fixed by symmetry. It's not very complicated. The last line, where I've got a sum over a matter of y, psi, h, psi, well, that's a lot of ambiguity. That's the sum over all possible matter fields with all possible couplings to the Higgs boson, and that's the sum over lots of terms, which is a lot of the stuff in the standard model is those parameters y, which I've just written by y. But it's constrained very strongly by several things. So Lorentz invariance tells you that a lot of terms have to be related to each other. There's group theory, because the way these forces are constructed is by Yang-Mills theories, and
Sorry, I think there's been a bit of an audio cutout, Neil. Oh,
really?
I can hear you.
When did you?
About 5 or 6 seconds ago. Just
okay. Sorry, I said my internet's not doing so well. Yeah, let me do one thing. If I really do disappear, I won't talk for hours. Send me an email. I'll take off my Wi-Fi. Okay. All right, so I was just saying, I don't know where I left off, but the last term is the sum, and it's a bit of a mess. You have to experimentally determine what all those y's are, and we'll come back to it because we're going to talk about the Higgs next. But group theory and special relativity, which is essentially another form of group theory, completely constrains this Lagrangian. And so conceptually, it fits on the side of a cup. But it's the fidgety details that make it a whole page. Okay. So that's just pointing out the various terms, as I said. So there's the strong, weak forces, the quarks, neutrinos, electrons, the Higgs boson, and then the final term is what's giving rise to the masses. That's the coupling to the Higgs. So H is Higgs, psi is a matter field. So everything was good, everything's discovered, and then in 2012, the long sought after Higgs was discovered. And there's the picture of the original. It's by now, there's much more data, but original discoveries. Actually, it's rather amusing. Those plots are not discoveries, they are failures to exclude. So what you're seeing is a line there, and that bump is where you have not excluded it. You have not excluded it, is that bump. And the same for there's two different separate experiments, CMS and Atlas, and they saw the same failure to exclude, the same bump at the same value of the mass, which is about 125 times the mass of a proton, 125 GeV. It's very important because it's the last piece of the standard model to have been that was predicted to have been discovered. It has this role that it's the origin of mass, but I will talk a little bit about that in a moment. It's not as dramatic as you might think. But also, there were serious controversies about it, and a lot of people thought that it may not be found, or if it was found, it would lead to a breakdown in the standard model. The standard model, it was often thought the standard model would start breaking down more or less once we start seeing the Higgs. And I'll explain that why. But first I want to debunk this claim a little bit that it's responsible for all the mass in the universe. That's not quite true. In fact, that's not remotely true. If you look at the hydrogen atom has, say, a proton and an electron around it. But the proton is 200 times heavier than 2,000 times heavier than the electron. And the proton's made up of 3 quarks, but actually it's the binding energy of the quarks that gives the proton the mass. The quark mass itself is just 1% of the proton mass. So of an atom, it's 1% of the mass pretty much comes from the Higgs boson. Most of it is just from the binding energy of the quarks. However, there's one very important feature, is that if you look at the electrons, all of the mass of an electron comes from the coupling to the Higgs. And that's very important, because if you study the Bohr atom, where you have a proton and then there's an electron circling it, naively, it's in a circular orbit whose radius is the Bohr radius, and it's written there, it's h bar squared over me squared. So m appears in the bottom. M is the mass of the electron. So if the electron didn't have a mass, you wouldn't have a Bohr orbit, you wouldn't have atoms, right? And so it's quite remarkable that we only understood 8 years ago why it is that an electron has a mass and why it is that an atom is stable, right, or exists at all. Right? So that, I think, is quite shocking. You can't just, in that standard model, you can't just add what's called a bare mass term for the electron. You have to do it through this Higgs mechanism. Okay, so yeah, let's go to the known unknowns. So that will lead us to talk a little bit about this Higgs mechanism. So these are the problems. So everything I told you before is just fantastic, right? Everything's rosy, everything's fantastic. We understand everything. We now understand the mass and why there are stable atoms. Yeah, there are problems. One is quantum gravity. We have said nothing about gravity. The standard model doesn't describe gravity. Well, it's okay it doesn't describe gravity because it's so incredibly weak. So if you think about 2 protons, these are the things they collide at the LHC where they discovered the Higgs. Well, 2 protons have electromagnetic repulsion because they're both positively charged. And the force law, if you recall, goes like the product of their charges divided by the distance squared between them. But since they have mass, there's a gravitational attraction between them. But that also goes like the product, it goes like the product of their mass squared divided by the distance squared as well. So it's the same, the force, the ratio of the 2 forces is independent of the distance between them. And so it's just some number, and that number, lo and behold, is 10 to the minus 36. So the point of that is that in order to have any kind of noticeable gravitational interaction, you need to somehow cancel off the electromagnetic force or get 10 to the 36 protons together, which is like the Earth. Right? You get something big, and then you'll see the cumulative effect of all those interactions from gravity. But if you just take 2 protons together, you're never going to see quantum gravity or quantum gravity. Of course, we have a beautiful theory of gravity due to Einstein. It's called general theory of relativity, where he says that gravity is the curvature of space-time. And since it's the only force that we're really aware of that exists on large scales bigger than, say, the solar system, it determines the structure of the universe. And Einstein's theory is also extremely successful. General relativity is very successful. It's even used, to make your GPS locators work. You need to take into account effects due to general relativity for the satellites orbiting the Earth. But it's notoriously difficult to combine this with quantum mechanics. So Next, there's the hierarchy problem. And this is an interesting problem. The standard model has about 20 parameters in it. Those like those Ys I showed you earlier. And they must be determined from experiment. They're just not, it's ultimately an empirical theory. You write it down based on symmetries, and then you go compare with experiment, and you read off what those parameters are. And all but one of them are just numbers. They don't have units associated with them. They're just numbers. And actually, those numbers themselves have quite a wide range from about 1 to 10 to the minus 6. So for example, if I go back, the mass of the electron is some constant y, so some small number times v. And what's v? V is the expectation value of the Higgs. So the Higgs is actually not 0, it's condensed everywhere. And it has a non-zero value everywhere in space-time. It's not, so it's everywhere non-zero. And it fluctuates about that, not 0, but it's everywhere non-zero. And it's that non-zero bit that's giving rise to the mass, and that's called v in this expression. And so the mass of the electron is some number times v. Well, that number y is, I don't know, it's around 10 to the minus 6. V has a scale, so let's go back to here. V, which is this value that the Higgs field mysteriously takes everywhere in the universe in its ground state, has an energy scale associated to it. It's not a number, it's got a scale. So it's got a units, if you like. And then it's important what the scale is. Excuse me. It very much depends on the meaning of the scale. So if I say a number that doesn't have units, 10 to the minus 6, that's small. Yeah, I think we can, it's small. For example, if you square it, it's much less than itself. But if a number has units, then you square it, it has different units, and you can't compare the two, right? So how do you know if something's small? So here's my example, money. Money comes in units, right? So is $1 million a lot of money? Well, $1 million, yeah, that's quite a lot of money. But $1 million Laotian kip is really not so much money at all, right? In fact, that's about $1 US, 125. Whereas, so I've got Bill Gates there, who's worth $1 billion. So that's 10 to the 9. And then there's this poor couple of children in Laotia somewhere who got, living on the poverty line of $1.25. So that's a scale difference of 10 to the 9, right? One part in a billion. And now that has meaning. The 10 to the minus 9 has meaning. That whether it's $1 million Laotian kip or $1 million by itself doesn't have meaning. You have to, the big thing that has meaning is the value of the dollar. So this is this V. V, it turns out, is 246 GeV, so it's about twice the mass of the Higgs. But what should we measure V by? What's the scale? It doesn't mean anything to say it's 246 GeV if you don't tell me what a GeV is. Well, the most natural scale in nature is the scale where gravity becomes important, because gravity, it's the product of masses, and there's this, and mass is energy, and there becomes an energy scale where gravity becomes important. Well, on those units, V is 10 to the minus 17. That's pretty small. It's really small. In fact, if you want to think about it, that's like having somebody as rich to Bill Gates as Bill Gates is to that girl in Laos, sorry, not Laos, Laos. So that would be pretty astonishing, right? Imagine if there was someone as rich compared to Bill Gates as Bill Gates is to this $1 a day person. I mean, that's really an astonishing ratio of numbers. So where the hell does it come from, right? What, in principle, we're supposed to have some theory of everything. We're supposed to be able to compute this, but it's hard to imagine it coming out of a simple calculation. And we often say such a thing is finely tuned. If it came out of a calculation, if there was any slight change in the understanding or the error bars of the calculation, you'd expect that number to fluctuate wildly. You have to really, really tune things to high precision to get it to be exactly that number coming out. So it's sort of analogous to, Here you have a pencil balancing upright, and to make matters worse, you've balanced an egg on it. Like, yes, this doesn't violate the laws of physics. It's absolutely fine. You can have a pencil standing upright with an egg balanced on it. Absolutely. That does not violate the laws of physics at all. But if you came into a room and you saw that, you would be suspicious that somebody had set that up. And so similarly, when people were looking at the Standard Model and this Higgs mechanism, which gives a rise to the masses, it's a bit like that. It's so finely tuned to make us have this low energy world. You would naturally think that, you know, the mass should run up to this scale where they're all of order 1, and then everything would be so massive there would be none of us. And there would be no low energy physics at all. So people thought that the Higgs was working, but would also kind of fail. And that's why they thought that when they saw it, it would start to deviate from the Standard Model. But so far it hasn't deviated from the Standard Model. Well, there's another problem. It's rather similar, actually. If you combine gravity into the Standard Model, or even just our understanding of physics, this has nothing to do with the Standard Model of particle physics, you can ask yourself, what's the vacuum energy density of empty space? How much does empty space weigh? In the Standard Model, which is a theory without gravity, it doesn't matter. The lowest energy state, the mass of it doesn't matter. If you think about potentials, you can move a potential by a constant amount. It doesn't change the physics. All that matters is the difference between potentials, between the top of the hill and the bottom of the hill. It doesn't matter where the bottom of the hill is. That's not true in gravity because energy gravitates. So when you say that the space has a energy density, that should gravitate, it feeds into Einstein's equations and it leads to a curvature of space-time. And it feeds into gravity through something called the cosmological constant. And so the mystery is, what should the cosmological constant be? Well, using the same arguments from before, you would expect the energy of the vacuum, I don't know, but it's around 1. In the units where the Planck scale, it's called, where quantum gravity is important, vacuum energy is probably around 1. That would be my first guess. Maybe it's a half. Maybe it's 0.3659246 times the scale of the vacuum. Well, that's horribly, horribly, horribly wrong. It's in those units, we now know what the cosmological constant is. We know from about 1998. And it's, I can't see my screen there. It's about 10 to the minus 16, is that 17? So that's another astonishingly small scale. It's roughly the same. Sorry, well, it's 122 then? I can't see, yeah, it's 122. Well, that's because it's taken to the 4th power. You can fudge these things a bit, but it's far off. Now you might say, well, maybe there's something special going on. Maybe it should be set by that scale V that we had earlier. Well, then you're still off by a huge amount. So if it was set by that scale V I mentioned, then it's 10 to the minus 68. But it's 10 to the minus 122. So this is like the world's worst prediction of anything ever, right? And this is a huge problem. We don't understand it. It's not a fault. It's not a miscalculation because it's possible that it is 10 to the minus 122. None of these theories are designed to calculate this number. You're just making wild guesses for what this number should be. And any wild guess is off by like 122 or some 68 orders of magnitude. Of course, I'm exaggerating because it's the 4th power. So if V was off by a factor of 10, then V to the 4th would give you a factor of 40. But anyway, it's a big problem. Another problem we have is dark matter. So that, by the way, this cosmological constant problem is often called dark energy. And so this V, the vacuum energy, or the energy, sorry, not V, but the energy of the vacuum, is often goes by the name of dark energy. But most people think that dark energy is a cosmological constant. But that is actually so the words, I'm using them interchangeably. If you want to be conservative, you should call it dark energy because you don't know what it is, but it looks very much like a cosmological constant. And no matter what, you'd have to explain why the cosmological constant is small, because it's something that's allowed in the equations, but empirically, it's extremely small, maybe 0 or close to 0 if it's the dark energy. Well, if we look out into the universe and we look at the way galactic curves work, that's the way the stars move around galaxies, they don't look as if they're following the mass that we see. There's these rotational curves for the stars in the galaxy, and of course you'd expect them to sort of get slower and slower as they fall out, but actually they don't. And this is indicative that there's more mass in the galaxies than we can see. So another great name, we call this dark matter, where it's on the assumption, or there's lots of evidence for dark matter, that there's stuff out there that's floating around and it's dark. I mean, we can't see it, which means it's nothing more than the statement that it doesn't interact with light. And theoretically, there's no reason not to have something that doesn't interact with electromagnetism. That's fine. And that would mean that you could never see it, right? Because to see something, you have to have the photons bounce off it. But if the photons don't interact with it, they just fly by. And so you would never see such a thing. But we believe that everything gravitates. So you would notice dark matter through its effect on gravitation. And that's how we're inferring it. We're using it to say that it's providing additional mass distributions in the universe beyond the visible light that we see from stars. And in fact, it turns out that 80% of the matter in the universe is dark matter. Right? And which means that 80% of the stuff that's floating around in the universe is not described by the Standard Model at all, as far as we're aware. Okay? So this fantastic theory, which is so precise and elegant and simple, is describing like 20% of the stuff in the universe. Okay? And I've got some pictures down there. There's a beautiful picture of the so-called bullet cluster. And on the left-hand side, you see the distribution in a blue color of the visible light. But then on the other diagram, it's what the distribution looks like if you look at gravitational lensing, the way light's being bent, of where the mass distribution is. And it looks like a bullet cluster. It looks like these two galaxies have flown through each other. Since they're not very dense, they've just passed through. But they're dark matter halos, the dark matter clouds linger gravitationally, and they do see the shock wave as they go through. But the visible light particles have just, the individual stars, which are like points, have just flown through each other. But the dark matter has merged and you see the shock wave. But there's many evidences for dark matter, but it's not understood. We do experiments to look for it, and we don't know what it is. We haven't detected it in any way or shape or form whatsoever. So there on the right-hand side is a little picture that shows the makeup of the universe. So if you compute the energy source in the universe, 74% is this dark energy, because it's this cosmological constant, which although tiny, it's everywhere. So it adds up. And that counts for 74%, 3/4 of the energy density of the universe. Then about 20-something percent, 22% or so, is this dark matter stuff that's lingering around in the centers of galaxies and it gravitating in. And then there's just that tiny little bit left, about 3 or 4%, which is the stuff of the standard model. So that's the bit we understand. The rest, well, that's the known unknown, if you like. Shall I just check what the questions are? There's too much for me to do in a medium time, so let me just continue. And then we can talk about these things in the chat later. There's some good questions here, but
yeah, that's fine. We can talk about them once the slideshow's over.
That would be better. We'll keep the flow. I'm just looking if there's any urgent questions, like, I don't know, my slides are done or something. Okay. All right. So now we're going to move into the last section, which is the unknown unknowns. So there's the stuff that we know, the stuff that we know we don't know, and now here's various ideas about what we think might be going on, but we don't know. And that 3 topics really: grand unification, supersymmetry, and string theory. So going back to the standard model, what's next? So physicists think in terms of energy scales. when we do these, particle physicists think in terms of energy scales. When we do these experiments at the LHC or whatever, we're smashing atoms up. We're cranking up the energy. Now it's the energy per particle that we crank up. The actual total energy in the LHC is not that much. It's like if all that stuff collided and formed into one mass, I think you get like a grain of salt or something out of it. It's the energy per particle that's so high. And we do that because the higher the energy, the closer the particles get and the shorter distances you're probing in terms of physics. So there's this diagram here of energy at the bottom and going to the right, higher and higher energy, which means we're going to looking about how physics looks at shorter and shorter distance scales. And on the left, I've drawn something called the coupling constants, coupling strength. So all these forces are governed by a number, which is roughly speaking how powerful they are. So if you like, for electromagnetism, it's E in certain units, the value of the electric charge. That determines how powerful how powerful electromagnetism is. Whereas gravity is described by G Newton, which actually is dimension 4. And then there's a similar number for the weak force and the strong force. So the point is that at low energy, these things are all different. They are what they are, but we know that they evolve in energy. They're not actually constants. They depend on the energy scale. Now, what's the energy scale I've drawn there? Well, there's 10 to the 3, which is roughly in GeV units. So 100 GeV, that's roughly where the Higgs is. That's where the LHC is operating, up to a TeV, so up to 10 to the 4 GeV. So to the right of that line, we don't really know anything. That's terra incognita. We haven't any experimental observations there, but we're trying. But we do see that these lines converge, and they seem to meet at some scale around 10 to the 16. And that would suggest a further unification, that these 3 forces unify, and possibly even gravity unifies later on. So that leads to the notion of what's called a grand unified theory, or GUT, G-U-T. And that would postulate that there aren't 3 fundamental forces. There's only one fundamental force. It's the GUT force. And you'd see it unified at whatever, 10 to the 16 times the GeV, 10 to the 16 times the proton mass. That's what happens in electromagnetism with the weak force. There's electromagnetism and the weak force, and they kind of unify. Mathematically, they unify, meaning that when you get to about 80 GeV, 80 times the proton mass, that's when the scale at which these W and Z bosons, that's their mass scale. When they become effectively massless, when they're light, then you would see a unification of the weak force with the electromagnetic force. And the idea here is something similar will happen around 10 to the 16 GeV, and that all those forces will combine with the QCD force of the gluons to one super force, you might call it. And mathematically, it's beautiful because actually we had these groups, SU3 times SU2 times U1, and all these particles form what's called representations of that group, which means they carry very certain charges and things with respect to various generators in that group. But they actually reassemble themselves up into representations of this other big group, SU5 or SO10, which would serve as some unifying picture. And it's remarkable, right? It's like as if I gave you a puzzle, or in fact, I gave you 3 jigsaw puzzles, and the pieces all fit in together, fine, made 3 pictures. But then I told you that, oh, well, actually, you can reassemble all those pieces and they'll fit together to make 1 jigsaw puzzle. That's striking. Yeah. And that's sort of what happens. You have SU3 and SU2 and U1. Okay, they're separate, but if you take all the particles together, they form what you need to make SU5. So these are the grand unified theories. And there's other evidence that they come in too, but I won't have time to discuss them. Then there's supersymmetry. So the standard model is based on a quantum field theory, which itself is based on the Lorentz symmetry of special relativity. And you can ask yourself a question. Could there be anything deeper than the Lorentz symmetry? The Lorentz symmetry is the symmetry of space-time. It's about rotations in space and then boosts when you rotate into time. You can ask a mathematical question, could there be anything deeper And the answer is yes, there's something. It's called supersymmetry. And it's a beautiful mathematical structure. And in that supersymmetry, the forces and matter are unified. So in the standard model, we had the force particles, which was the gluons, W's and Z's, and the photon. And then the matter particles with the quarks and leptons, the quarks, neutrinos, neutrinos, electrons, muons, taus. Supersymmetry forces you to rotate these into each other, if you like. So they become all facets of the same thing. So what of course, they're not all facets of the same thing. So what supersymmetry immediately does is it tells you that there must be hidden particles we don't see, which are the superpartners of all the particles we have seen. So in a click like that, if you postulate supersymmetry, you double the number of particles you think there are. But then you can combine them into these gut models and it actually becomes relatively elegant. But it's also very nice because it provides a natural candidate for dark matter. It helps the gut models. This is circular reasoning, if you like. None of this is scientific, you must have it. But these are nice things that happen if you do have it. So it makes the gut models work better. That running of the couplings works better in supersymmetric models. They meet at a point more accurately. It provides a natural candidate for dark matter, because you have just postulated a whole distant family of mirror particles, and we don't see them. But it turns out that the lightest one must be stable, and it would just be out there floating around, doing nothing. Well, that's dark matter. So it's a good candidate for dark matter. And one of the main impetuses is it's very helpful for the hierarchy problem. So you're still entering a room and you're still finding yourself with a pencil with an egg sitting on top. It doesn't change that. But now, it's like you'd go and you'd see, oh, it's been glued. So it's a little less remarkable that it's standing there. It's still surprising, but it still indicates you may not understand something, but it's not the desperate situation of it being finely balanced. It's more rigidly stuck. Although that's only true if supersymmetry is discovered relatively soon, and actually people are starting to lose faith in it because it's already not doing that job so well. So my last slide, I would want to mention the real extreme, which is string theory. And so there's this XQCD slide. But we know a lot about string theory. It's been the dominant thing we study in theoretical physics because it's a very, very powerful framework for doing quantum physics as a mathematical playground to think about physics more generally. So a string is exactly what you might think it would be. It's something that vibrates, it's one-dimensional. Just go back and do it again. So those are 3 vibrational modes of a string. But in quantum theory, when you quantize waves, like those waves, you get particles because of wave-particle duality. So if you had a string, each one of those vibrational modes would be interpreted as a different type of particle. And it's beautiful if you quantize a string. You take a string, you add relativity and quantum mechanics, and you just quantize it. You just consider the quantum theory of that string. And you will find that it produces particles that look like the standard model particles along with gravity. Gravity comes included for free. You didn't ask for it, but it comes in. And in fact, it turns out to be a finite theory of gravity, which is one of the problems of quantum gravity. But there's another miracle, which is if you know of a string, a single string, once you know a single string, you know its interactions. And the reason is the following. On the left-hand side, I've drawn pictures of particles coming in. These Feynman diagrams that we saw when we were discussing quantum field theory. That you can imagine 2 particles coming in, meeting at a point, and coming out. Or the bottom one is the 2 particles coming in, exchanging a virtual photon and going out again. If all those particles are replaced by strings, then you get the string diagrams on the right. And they're perfectly smooth, nice manifold structures. Whereas, the diagrams on the left with lines, they're lines, and then there's this point where something happens. And it's the point where something happens that you have to tell the theory what happens at that point. That Lagrangian, that big Lagrangian I was showing to you, is basically an instruction for what happens every time 3 particles or 4 particles meet at a point. And it's arbitrary to some extent. That's the 20 parameters of the standard model. And these are just different ways of which you can do this. But strings, you see, this is all very smooth. And actually, if you look at those diagrams and you cut them, that it's always just one string. If you cut it, it's just one string everywhere. And you know what one string does. So actually, string theory is very constrained about what the possible string interactions are. They're not arbitrary, it's fixed. So it's more or less unique, except there are prices you pay, one of which is you have to have supersymmetry. But the other is you have to go to 10 dimensions. And then there are only 5 possible string theories. But they're mathematically complete, we think, and they involve quantum gravity as well as the forces like the ones we see in the Standard Model. To be fair, of course, there's no experimental applications yet of string theory, but it has had a great deal of mathematical results and also results for physics about trying to understand field theories in general. But it gives us a quantum mechanical theory of absolutely everything, although arguably that's its weakness. It's everything and more, because you're up in 10 dimensions. And in fact, it turns out it's not just 10 dimensions. There are 5 of them in 10 dimensions, but then it was realized that they unify themselves into 11 dimensions, where there's one known theory in 11 dimensions, which we call M theory. And the price you pay is the following. So particle physics, you think of a point particle and it moves through time. And so there I've drawn the world line of a point particle. And if you quantize a point particle, you can do that, and you'll get some basic features of particles, but it doesn't tell you about the interactions. And then you have to do quantum field theory to put in the interactions by hand. If you take a string, you just have to postulate that the string exists, and you quantize it, assuming quantum mechanics and Lorentz symmetry. It does know about the interactions. It does tell you a lot about what must be going on in the space-time. So it's not, and then you learn that actually, by thinking more deeply about these things, because it's very complicated, right? You can't just solve the equations and claim to know everything. So for the longest time, people thought that string theory was only about strings, but then we realized that string theory contains these other objects, higher dimensional things, with world volumes that are 2-dimensional, 3-dimensional, 4-dimensional. We call them p-branes. And you realize they're there by looking at the strings. So once you postulate the string and you quantize it, it opens up this whole world of possibilities and things that must exist. And the string is just one of those many things. It's the one that you use to do the calculation with. But once you do the calculation, you can see that there's these bigger brain-like objects all lifting up into 11 dimensions. And that's sort of the rough guess to why we're thinking about 11 dimensions and these objects called brains in 11 dimensions. And my last slide, sort of go full circle, is this famous ADS-CFT correspondence that people may have talked about, which again came out of string theory, but in some sense is a little independent. It turns out that if you have a string theory, or theory of quantum gravity in a bulk in a background called antidecisive space, which is a rather strange space, it's a space with a negative cosmological constant, not the positive one we see. Then that's the same thing as a quantum field theory on the boundary, one less dimension. So now we're finding that, again, it's the story that gravity and quantum field theory are unified. I mean, they're 2 aspects of the same thing. And this is a truly remarkable correspondence. It's a lot of research goes into it. And actually, it's even starting to have practical applications, because it turns out it's just an interesting toolbox you can use to try to solve problems in more conventional situations like condensed matter physics, for example. So it turns out you can study superconductivity by thinking about black holes in 1 higher dimension, in 5 dimensions. Well, 4 dimensions, because superconductivity is not plane. Anyway, that's all I've got prepared. I hope it was somewhat coherent. So I'm going to stop here, and maybe we should address the chats.
I'll turn on the camera.
Hi, thanks, Neil. That was a really brilliant talk. So yeah, we can just go to the chat, and there's quite a few questions, so we can get stuck into them.
Should I just start from the beginning and go through this? Okay, well, I think I said some, but let me just go over it again. So the first one, the particle that mediates the weak force, that's these W's and Z bosons. What is the cause of the weak force? Well, it's particles will come in and they will spontaneously emit a W boson, which is then absorbed by some other particle over there. So what happens when, for example, beta decay is you have an up quark, and it's flying along, and then it spontaneously emits one of these W bosons, and it turns into a W boson carries electric charge. So the up quark, which is charged 2/3, I think I could have my numbers the wrong way around, but 2/3, it emits a W boson, so it goes to -1/3, and that's a down quark. So an up quark will turn into a down quark and spontaneously emit a W boson. Now the W boson is a virtual W boson, so it goes a little way, and then it breaks up into an electron and a neutrino. So the in state might be a up quark, but then this process happens and the out state is a down quark, an electron and a neutrino. And that's beta decay, because if you put that inside a nucleus, that turns a neutron into a proton. That would turn a proton into a neutron, excuse me. And an electron flies out. And then you had the neutrino flying out as well. But microscopically, it's just one quark turning from an up to down quark and releasing a W. Yeah, I'm going to skip some of the questions because I think that they're time sensitive to my talk. So the electroweak combination coming. So it turns out mathematically that the weak force itself is described by group SU2, by the W and Z boson, and the electromagnetic force is described by what's called a U1, which is just described by photons. So there's 4 particles of force there, the photons, the Z, W plus and W minus. But actually, mathematically, they all combine into one type of particle. At scales of about 100 GeV, you would just see one particle, which then at low energy becomes the W plus W minus Z in the photon. And that's through this Higgs mechanism, which I didn't explain in detail. How did Einstein predict about the EPR paradox? So let me postpone that for a little later because it's a separate issue. To remind me if I don't answer it, it's not directly related to talk. How at WZ? Quantum mechanics, everything sort of happens. You can't stop it because, roughly speaking, you have the Heisenberg uncertainty principle that tells you that nothingness is not possible because there's always an error in the uncertainty. So there's always delta error in position times the error momentum is bounded. So something has to happen, otherwise you violate Heisenberg. So this lowest energy state we call the vacuum state, the vacuum. The vacuum is not nothingness at all. No, no, no. Things are popping out of it all the time. And then they just disappear again. Pop in, come out, do that. But, well, sometimes they don't disappear. Sometimes you observe them, or they can be exchanged. And that's what these, so if they're exchanged, that's what's called a virtual particle. So it's sort of, its existence is somewhat inferred. It takes momentum, say, between 2 electrons, and you don't observe the intermediate particle itself, because that would violate energy conservation. But there can be situations where you just, if you add energy to the vacuum, you will pop out particles out of it. All types, in a random way. Well, yeah, in a more or less random way. And the vacuum itself is doing that all the time. Which one? All right.
What did you say?
Subatomic level, either energy or particle. I don't understand that question. So which one is more vital in subatomic level, either energy or particle? What would be the properties of antimatter of Higgs boson if we discovered it? You mean the anti-Higgs? The Higgs is its own antiparticle. And the Higgs, of course, is very, very unstable itself. So all those particles have antiparticles. Well, some of them don't. The photon is its own antiparticle, the Higgs do. Actually, the Higgs. Yeah. So one of the big things, I think this is another person's question, is why is there matter over antimatter? So indeed, these theories predict an exact, or almost exact, symmetry between particle and antiparticle. So you have the electron negatively charged and the anti-electron, the positron, positively charged, with the same mass. And when an electron meets a positron, they just annihilate into light and disappear. The energy is carried away by light. So it begs the question, why is there anything left? Because all the matter should annihilate the antimatter, but it obviously hasn't. So what you have to postulate is that, at least in the initial condition, you need two things: that there was an imbalance between matter and antimatter in the initial state. And then you need some kind of slight asymmetry, and there is in the Standard Model. There are some asymmetries between matter and antimatter. Well, it's called CP violation. And actually, there is some vague evidence for this in the universe. So the universe is by and large empty, right? The matter of the antimatter has annihilated. It's left in the planets, but the radiation density is much higher. So there are 10 to the 9 photons for every proton in the universe. And that's indicative that there was a lot of matter, antimatter in the universe, and it annihilated, so that we actually only see 10 to the minus 9 fraction left of matter over antimatter. So it is consistent with this idea. But it's not fully understood, by the way, by any means. Is it necessary to find quantum gravity? Yeah, I think it is. I mean, we've had all these really exciting discoveries in the last few years about black holes. I mean, they're coming at the rate of major revolution like every year. And there we're going to need, at some point, we're going to run into quantum gravity issues and conceptual issues. And it's really, yeah, maybe in 50 years, we're going to really be seeing some stuff there, I think. And that's really exciting. We have mass and gravity related. Why is Higgs not related to gravity? Well, the Higgs is the origin of mass for these particles. But as I said, it's only a little part of the mass. So it gives the electron almost all its mass. But most of the mass in the universe comes from like this binding energy of the quarks. And gravity, it's sourced by energy and matter of any kind. It's actually rather blind to the origin of it. So the Higgs is not responsible for much of the gravitational physics in the world. And any energy gravitates. Something about bending. So I won't read it, but so light does bend in gravitational fields. That was one of Einstein's predictions from general theory, relativity. It's called, well, now we call it gravitational lensing. And if you Google it, you'll see some amazing photographs because it's seen very clearly in pictures of astronomy. So indeed, when light passes by the sun, well, the classical explanation of Einstein is that the sun bends space-time, makes it curved, and so the particle will deflect, the light will bend, it will deflect, because it actually follows a straight line in the curved space. And that was observed not long after Einstein's theory. Quantum mechanically, you'd say that a particle of light, photon, passes by the sun, they exchange virtual gravitons, and that causes the bending. It's quite a dramatic effect. I mean, you've all seen this picture. I forgot my phone. Hold on a second. So I thought this would be quick. You've all seen this picture of the black hole?
Oh, yeah.
Why is it a ring shape? It's got an accretion disk of stuff flying in it. Yeah. So that's all the stuff that's falling in and heating up and emitting light. But why do we see the whole disk? Are we just lucky that we happen to be looking down the axis? So that the black hole is here, the accretion disk is going like this, and we're looking straight down, almost straight down, the axis of the rotation? No, it's bent. This bit is duller because it's the back, and it's bending around the black hole. So the light from the top is being bent around the black hole. You're not seeing it head on, you're seeing it sideways. It's an angle like that, but it looks head on because the light from the backside has been bent by the black hole, so that it looks like it's on top. So have a look at that. That's really exciting. There's these great simulations, and if you saw the movie Interstellar, those calculations that went into there were actually done by the guy who got the Nobel Prize for, not for the Event Horizon telescope, but for the gravity wave detection. Okay, but there's also, you see it with the gravitational lensing with stars, you get multiple images too of stars because they've all been bent around some that big source. So some they go this way or that way around. Yeah. Sometimes I wonder if gravitons are just baloney. Well, yeah. Me too, but I think they're there. Okay. Science is too dysfunctional for coming to terms with this. No. Science is an adventure. It doesn't always work, but that's the adventure. Can you please explain about the term rest mass of the photon zero? Yeah, so when we talk about mass, what do we mean? We actually only mean one thing, and that's the rest mass, which is to say you have to go into the reference frame where the particle is not moving and weigh it, or whatever you want to do. It has energy. It's the energy of the particle in the frame where it's not moving. That, if you like, defines its mass. That's called the rest mass. If you take some courses in relativity, they might talk about an effective mass or a position velocity dependent mass. Yeah, it's really, there's only one concept of mass, which is you go into the rest frame and you compute the energy of the particle. That's its mass. E equals mc squared. And more generally, E is mc squared plus momentum squared. It's all square rooted. That's what it means, the rest mass. It's that. Now, if the rest mass is zero, if this, that can't be, then you can't actually, so light doesn't have a rest frame, it's massless. It does something very different. There's no frame of reference in which light, this mass, is stationary. That was Einstein's big idea. So you can't define its rest mass, and in fact, it has no mass. Its energy relation is not E squared is m squared plus p squared. It's just E equals p. There's no mass contribution to it, and there's no frame in which it has a rest, in which it's not moving. How do we come to a conclusion based on the coupling strength that there must be unification? It's not a conclusion. It's a guess. It's an inference. I think I answered the antiparticle question. Yeah, it's the known unknowns, if you like. There's something happening. We think it could be this, but we don't know. There are other reasons, by the way. It's not just the forces, those coupling constants unify. As I mentioned, it's like these jigsaw pieces that suddenly reassemble in, three different jigsaw pieces that reassemble into one picture. That's quite striking. So you might think that that's good. It also predicts another quantity known as the Weinberg angle pretty well. But actually, there are problems with gut theories. One of the most robust things about a grand unified theory is it predicts that the proton will be unstable. So the reason why you and I are made out of protons and neutrons, well, neutrons slightly different, electrons and protons, is because they are the lightest particles that carries a conserved charge. So the proton, so the electron, is the lightest thing that carries an electric charge. So it can't decay because there's no known particle which will carry that electric charge, which is lighter than it. There's only things that are heavier than it. So that stops it from falling apart out of principle. Proton carries another charge called the baryon number, and it's the lightest particle that carries the baryon number. So a neutron carries a baryon number too, but as we've seen through beta decay, it decays into a proton. And the proton has nothing it can decay into because this thing called baryon number is conserved. Well, in a grand unified model, baryon number is not conserved. So we expect protons to decay. And they've looked extensively, and protons, no one's seen a decaying proton. The bounds on these things are like longer than the age of the universe by far. And that puts constraints on these gut models, and it's intention. Yeah, it could be that the whole idea is a bad idea. String theorists don't understand that all masses can be simply derived from charges and the strength of the forces. I don't understand what that means, frankly. There's no derivation of the masses, they're simply observed. So they come from the coupling to the Higgs boson, and then these Y coefficients. And as far as I'm aware, nobody's ever computed these Y coefficients. They are just experimentally determined in anybody's theory. Hawking says God particle could wipe out the universe. Why? So there's something deeply peculiar. There's another peculiarity about the Higgs boson. So we live in a very strange world. It turns out the world is very just so. So I did delete the slides to explain the Higgs mechanism. But what it is that there's a potential for it, which is a double well potential. So it goes like that. And so the minimum energy is where it sits out here, not at the origin. The origin is a local maximum, and the energy is down here. Actually, I can, if you know the math, I can show you in the slide. This, you see my screen? This is the potential of the Higgs potential. And it's a quartic potential. It's h squared minus v all squared. So it looks like that. And so the minimum is where h equals v. That's what I meant by saying that the Higgs field has a value v everywhere. Well, there are quantum effects that come into play. And this is just the classical Higgs potential. It turns out that it'll grow another minimum. And that another minimum will happen at some large value of the Higgs field. It's it's actually just up by the, just below the Planck scale, just up by the Lagrangian, way up around 10 to the 16, 10 to the 17. Which means that it's conceivable that the minimum we're in is not the global minimum. It's a local minimum. And that means that due to quantum effects, you'll eventually tunnel out and you'll go to the global minimum through a quantum tunneling effect, which means that our universe is ultimately unstable and will decay. Possibly, there's a lot of extrapolation to go up that far. But as is, it's quite possible that the Higgs boson means that we're in what's called a metastable vacuum. It's possible. It's also possible we're not. And by the way, it's all, the lifetime for this, the predicted lifetime for the universe is, of course, obviously at least another time or 2 times the age of the universe. It's not going to happen next week, but it might happen in 13 billion years, or probably way more. That, yeah, the universe will just, because the Higgs boson will find the true vacuum. But don't lose sleep over that one. What are the experimental matches with theory till date? Well, that's a long list, long list. There's a book, which you might want to see, what's it called? Particle Data Group. You can probably just Google it, and there's just pages and pages and pages of measurements of values of things, of all these experiments. We certainly don't have evidence of string theory. Are there any predictions made by string theory that are theoretically possible to verify but aren't practical? Well, of course, one prediction of string theory would be that if you looked small enough distances, you'd see the string. Well, the strings come with a spectrum. It's a violin, and a violin has notes. And the notes are staged in a very particular way, right? They come in harmonics. They're not random, they're harmonics. So a string would have not a random spectrum of particles, but very ones with certain spacing. So if you saw that spacing, you would include strings. But of course, that would require super high energy, like crazy high energy. There are other predictions. Well, it's an essay question, really. Are there supersymmetry? If we saw supersymmetry, that's a big part of string theory, but it's logically distinct. Extra dimensions is part of string theory, but logically distinct. Yeah, I mean,
Atrai bisi dekai. Atrai bisi dekai.
We'll try to mute that. I don't know where that's coming from.
Yeah, raise camera.
Someone's domestic. Could Theodore Kluser-Klein's addition of another dimension to Einstein's be another contender to theory of everything? Well, yes and no. So string theory takes that and incorporates it because we have 10 dimensions or 11, it's M theory. So it very much relies on the Kluser-Klein idea. In fact, it predicts it. Now, Kluser-Klein by itself is not thought to be good enough. The problem is that one thing I haven't discussed is these models are mathematical models, but they're what's called effective models. We don't believe that they can be valid to arbitrary energy scales. We feel that they mathematically can't be valid. They break down. They have these divergences in them. And they only make sense if you think of them as effective field theories valid below some scale. And then you need some new physics that's valid above that scale. String theory purports to give such physics. If you just throw on another dimension, you're worse. It's not valid to high enough energy. It'll break down. You'll still need to add something more, as far as I'm aware. And string theory is the only known thing that does that. Okay.
Let's answer one of the questions. It says here, is it recording? Is there a link to watch this lecture again on YouTube? Yes, this is currently live streaming on YouTube and the lecture will be saved there after, so it will be accessible.
And also, if anyone wants to ask a question, you can unmute them.
Yeah, also, I'd just say, if anyone wants to ask a question with their mic, if they just put it in the chat that they want to be unmuted, we can do that. So that's an option as well.
I see another question we can knock off. Are dark matter and dark energy the same? No. So dark matter is this stuff, it's matter, it's floating around the universe. It clumps around, it's matter, so it gravitates, and it clumps around big things like galaxies. But it's not far away from galaxies, you don't expect to see it. Dark energy is energy and it permeates the whole universe. It's sort of massless, if you like. It's just the vacuum energy. Well, it's usually interpreted as the cosmological constant. So it's like the energy density of empty space, and it's everywhere. Tiny, but everywhere. I can't answer this question. Is it possible that the space-time fabric is made up of dark matter? If no, then what would be the building block of space-time fabric? I have not, some questions you don't ask yourself in science, like what is this, what makes up space-time? I mean, it's a great question in a way. I don't mean to belittle it, but I have no idea how to answer that question. What is space-time? That's a deep question, ultimately in quantum gravity. Because we don't, when you take quantum gravity into effect, we don't really think that there will be a classical notion of space and time. It's some kind of derived concept that's come out at low energy. It's not actually intrinsic to the universe at all.
Group have a lot of questions. Can you turn on the
Give matter its most mass or all its mass? So actually, as I said, the electron gets all its mass from the Higgs, as does the muon, the tau, but the quarks, and hence the protons, and well, the quarks get their mass, but the protons, no. Most of its binding energy from the gluons, and so actually about 1% of the mass of anything physical is coming from the Higgs. Physicists look for the key where there is light rather than where they lost the key. String theory does make that up. Well, we certainly have to look where the light is because we don't have any other tools. I agree with that. But I disagree with the sentiments, right? To me, I would say string theory is the most natural, the simplest extension of what the ideas are. It's really only got two ingredients, which is special relativity and quantum mechanics. All you have to postulate, and it's just a small postulation, is that there exists a string that you can quantize. And then the rest falls, and then you see the structure. But that's it. If you do something like loop quantum gravity, which is a scientific subject one can study, you have to do significant manipulations of the quantum mechanics of the system to get it to work. And so although you're saying, oh, my only ingredient is general relativity, but we don't actually think general relativity is fundamental. But, well, that would be my point of view. We can have a rational debate about that.
Oh,
and string theory may well be wrong. Of course, it absolutely may well be wrong.
Oh, yeah. So I think we have someone who wants to unmute their mic. So,
Hello, Professor. So I have one question regarding the difference between the Casimir energy and the total vacuum energy. So the Casimir energy comes from the electromagnetic origin. So while calculating or assuming the total vacuum energy, do we also consider the origin of the electromagnetic, like the energy that comes from the Casimir effect?
Right. So this is a good question. So there's this so-called vacuum energy I've been talking about, which is just everywhere. You take it's as if you would if you could pick up a chunk of space and just weigh it. What would that be? It's poorly defined, huh? And that's one of the problems. And then you have to include the contributions from every type of particle there is. And so you have to sum up, basically, in quantum mechanics, things are described by harmonic oscillations, roughly speaking, by things that just fluctuate in a Gaussian way. They all have a ground state energy because you can't have zero energy in quantum mechanics. Well, there's a ground state energy which is not zero, but it's not meaningful without gravity. But each particle gives some contribution to the ground state energy. Each mode of the particle gives some contribution to the ground state energy. So you have to add them all up, and that gives you the vacuum energy in principle. Now, how you do that is a long and torturous thing because you don't even know what all the particles are, so how could you add it all up? And it's probably divergent, you'd have to regulate it. Okay, but that's, for the vacuum energy, every particle contributes. From the electromagnetic field to the quarks, you name it, they will all contribute. Similarly, you have this other thing, which is the Casimir force. Now, the Casimir force is actually quite different. It's when you have quantum field theory, but you put boundaries, so you've got like two plates. And so it's very important about the boundary effects of the plates. So you're not weighing the space in between. It's a very subtle calculation, actually, about the modes that exist between these two plates. Yeah? And then, indeed, you have a similar thing where you should be summing over the particles, the light particles that can be communicated between them. But there are big subtleties about the boundary conditions, which change it. So it's slightly different from weighing the stuff in between, but it's sort of conceptually the same. So it creates a force between two plates. But of course, you have to isolate the field so it's not on the other side of the plate.
Yeah.
It's a good question too. How is it possible that strings are even much, much smaller than the Planck length? So string theory is a tool. It allows us to calculate, and what we see from string theory is something much, much more than string theory there, which we call M theory. The tool we really exploit in string theory is the following. The strings have a size. If that size is smaller than the Planck length, then you will reach quantum gravity before you see the strings. And then you really don't know what the hell you're doing, right? Everything would become quantum gravity and you'd never see strings. Even though, so string theory could be totally correct, but you'd never see strings precisely because strings are smaller than Planck scale and you see quantum gravity before you see strings. But as for us, in the theory, we can tune it the other way. So we can work in a regime where the string length is large compared to the Planck length. So we see strings before the Planck scale. And that's what allows us to do any kind of perturbative string theory computation, is that we have to work in a regime where strings are bigger than the Planck scale. But that's a limitation of our calculations. Sometimes we can do other things, but for a given, so string theory, it's badly named because it's only string theory when the strings are bigger than the Planck scale. When they're smaller, we call it M theory. We still call it string theory, but it could behave very differently from the picture that I gave you. we don't actually believe in this picture of vibrating strings as fundamental. I like to view it as a window. That if you allow me to make the strings bigger than the Planck scale, if you posit that they exist, then I can quantize them and I can see everything working. And then I have to extrapolate beyond that using various techniques that we have, but not so well.
Yeah, Finn, you can ask the question.
Oh yeah, Finn, you can ask a question. I think your mic's on.
Can I be heard? Yeah.
Yeah.
Okay. So I'm just wondering, given that dark matter doesn't seem to interact with light, first, well, it's sort of two parts. Does that imply that it just doesn't interact through electromagnetism at all?
Yeah.
If that's the case, then what possible forces could stop it from collapsing into a black hole?
Great.
Well, yeah.
So it's often referred to as weakly interacting dark matter, WIMPs. So there's evidence that it interacts through the weak force.
Okay.
Indeed, if you had it only gravitating, you'd have to do some work to stop it collapsing. But maybe it does just. I'm not an expert enough in the field to know what those models would be like. Okay. But most people think in terms of it does interact with something, WIMPs. Sorry, the weak force.
Okay then.
And
I'm
it could
just
have
wondering.
its own forces. You know, it could have its own QCD. It could be.
It's just like, given how much dark matter there seems to be, if it interacts gravitationally as it does, there'd have to be, well, a strong force, some kind of force that is relatively strong, keeping it from collapsing. Or so it seems
the
to me.
gravitational force is very weak. So but indeed, I think
scale-wise, since there's so much of it, given how gravity in the case, say, of a black hole can beat out all the other forces simply due to the the fact that there's no repulsive component.
Yes, so the electric force, which is the next best force we have experience with, of course, cancels out, roughly speaking, on atomic scales, right? And most substances are uncharged, even though they're made out of atoms, which have an electric charge on the outer shell and a positive nucleus core. Of course, we do see some effects of electromagnetism, lightning, static electricity, when that imbalance is ruined. And that cancels off very directly. But for gravity, yeah, you need the 10 to the 36. Now, to see some kind of effect of gravity over the other forces. So I'm not an expert enough on dark matter models to know how they stop them against gravitational collapse, but they must have some kind of ingredient like that.
Thanks.
Hi, Karen.
Hello. The question I'd like to ask is there no be able to verify string theory, or how big would it have to be?
Big. I mean, solar system sized? I don't know.
Solar system, did you say?
Solar system sized. Big. But under the traditional view of string theory. But I have to say, I mean, we don't understand string theory enough. To say that it has such a conclusion, like, oh, if you look here, you'll see strings. It's a very robust thing. It predicts lots of stuff, and it's not clear that it has. I actually think this is a strength, but from a scientific point of view, it's got an obvious weakness. Is that it's a machine for producing theories, which are mathematically consistent. It does not immediately land us on our universe or our set of physics in any way whatsoever, as far as I can tell whatsoever. So it hasn't got any robust predictions yet that I can think of. So like even that statement I said earlier, like if you saw strings vibrating with a spectrum of strings, yes, then you'd say I have a string. But if the Planck scale is lower than the string scale, you'll never see strings. the string theory would still be correct in some formal sense.
Thank you.
So I think we'll go to a question just from one of our board members, Rajarshi, who is sitting here.
Hi, so I'm Rajarshi.
Same room, that's rare these days.
So yeah, I was asking, like, you know, like theoretical physics is getting more and more like interesting, but at the same time, like getting very, you know, complex, because there are so many like fields that are getting so much like, you know, in deep things. So does that like discourage like creative and young minds to do research at like very early age? You know, like if you go 100 years back, there are people who can do research with much less background, but nowadays it's like you need to read up to, you know, like PhD level to study research. So what do you think of that?
Well, yes, it's like that. This is the advance of science in a way, is that it's produced such a body of substance. And this is true of all the sciences, I would think. But some of them more so than others. So one of the difficulties we have in theoretical physics is that it was so successful, and it's in two ways. One is obviously its connection with experiment, which has been just unprecedented by other subjects. And in a way, that's because it must be the easiest science, right? Biology is much more complicated. You don't have a fundamental theory that allows you to make robust predictions accurate to 13 decimal place accuracy. Yeah, that's because it's hard. Parts of physics are hard. We don't understand QCD. The other thing about physics is its tight connection with mathematics and mathematical rigor, which allows us to understand, well, which we think allows us to push the boundaries so far. So that's why you can talk about something like string theory, because it's based, its reasons for being, our arguments are based on mathematical rigor, not on physical observation. But we now see that there's huge discrepancies between, say, theory and prediction. So the gravitational waves predicted in 1916, observed, what, 4 years ago? And the black holes, the work, the Nobel Prize this year to Penrose, for example, for a theorem that he proved in the 1960s. And even that theorem isn't, it was great work. I'm happy for the prize. That theorem doesn't say there are black holes there, go look for them. It just says that they're robust. You should trust. You should trust it. So yeah, but I imagine it's probably getting similar in other subjects too. But there's also great areas of excitement. I mean, the gravitational waves, that's really a hot area. That's going to lead to a lot of interesting experimental results in the next 20 years, 30 years.
Yeah, thank you.
So one question that I have, which is actually just kind of linked to what you were just saying, is this thing that the physicist Eugene Wigner titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." So it's this idea, like with the Higgs boson, for example, the theoretical models that we had, the mathematics actually predicted the existence of this thing before the experimental verification was there. So I guess it kind of links into like, why do you think there is such a close correspondence between the sort of theoretical mathematics and the physical reality? And do you think that we can actually just have faith that the mathematics will lead to correct predictions and then just wait for the experiments to catch up?
Yeah, I do. Of course, you need the guidance, because I think one of the lessons we've learned from something like string theory is that you can take the lessons of mathematical rigor, and let's just suppose that string theory is rigorous, or will be proven to be rigorous at some point. Let's just give us that assumption. That doesn't mean it's providing the answer. It's just a formalism that allows you to speak where the answer might be, or to a question. I often think of it as a bit like 19th century physics. A lot of 19th century physics, development of Hamiltonian mechanics or Lagrangian mechanics, they were developing a formalism. The theory of the world is a particular example of a dynamical system that you can study using Lagrangian techniques or Hamiltonian techniques. Similarly, one might think that the theory of the universe as a whole is a subject that can be discussed using the language of something like string theory. But there are many other things that encapsulate string theory that you would never see. And whether you give that physical reality by, say, the multiverse or not is an interesting question, and a philosophical one. If you want to get philosophical, I mean, you could question what is reality anyway. I mean, it's just this weird classical perception that we all have. we know that the classical world is a fake. That's not really what the universe is doing at all. Maybe the universe is just some simulation of mathematics, and that's it. That's why it's described by mathematics. It is just mathematics. The classical world is the fake. It's the illusion.
So I think we'll wrap things up quite soon, but just got a couple more questions, and then we can wrap things up. The first one is, what advice would you give to, say, high schoolers or undergraduates who want to maybe go into research, be the scientists of the future, and they're just thinking, okay, how do I achieve this? How should I go about, getting involved in research and getting a PhD? Like, what would be your advice to people wanting to do that?
Of course, there's the usual work hard, study hard, but make sure you're enjoying it. It's not, you've got to find something you enjoy doing that's going to be worth your time to put in, because you will need to put time in. And it's no fun if you don't like it. And keep it as open mind as possible, because what is the hot topic? If you're an A-level student now, and you're going to go into university next year, and then you're going to do 3 years undergraduate, say, 2 years master's, 3-year PhD. You're looking about 10 years down the line. What will be the interesting scientific questions? It will depend on several factors, which will be, what are the opportunities available to you? What are the developments that happen in the field between now and then? And as well as, what are your interests? So, and they might be quite different, and sometimes you might go down a different path than you expected to go down, but that can be just as rewarding. It's really, you have to keep an open mind, look around you, think what are the interesting questions, and of course, what are to some extent, what the job opportunities will be when you come out. But usually, people find themselves driven passionately to do one thing, and that's what they do.
I guess one thing I'll ask slightly related to this is, do you think that there's still room in research for, I guess, what are termed like lone wolves, like Andrew Wiles types who work on their own and come up with a theory by themselves or proof by themselves? Or do you think that we've sort of moved into this era where collaboration has become a necessity? Because I guess one thing that I read was this criticism of the Nobel Prize, where it says, look at these great singular figures, and that kind of hides the collaboration that goes on in the background. Like,
yeah.
What's
well, it's both. So it is a collaborative effort. I mean, I saw a colleague of mine once method an analogy. So for particle physicists, so there's a little girl, she's lost in the woods. 1,000 people go looking for her. One person finds her. So who's the hero? I mean, are all the others useless? No, not at all. I mean, it's a collaborative effort, and one person stumbles on the right thing. Of course, some people have a record of stumbling on the right thing quite a few times. So there are still individuals. Science is more and more collaborative because it becomes bigger and bigger scale. Although there are always visionaries in that. There's all these big experiments that now have, anything from 300 to 3,000 people working on them. They have leadership that's been working for 15, 20 years to get that experiment done. But yeah, it is collaborative. In principle, you could play a very important role in science because of the questions you ask, the feedback you give to your colleagues, and yet you never have a result of your own. In principle, but that's not the way the market works. You're supposed to produce papers, and how you evaluate what is a good scientific outcome is tricky. Because maybe you're relevant in 40 years, maybe you're never relevant. Maybe you're really relevant for a short time on stuff that nobody cares about later. All these things happen. Yeah. And there's certainly still lone wolves, but they're never that lone. I mean, Andrew Wiles, of course, was a professor at Princeton, and he was just working on a project by himself. But of course, he was actively engaged with his field all the time.
So I guess we'll finish off with the last question. And I guess just living in the current time that we do, this idea of misinformation and scientific illiteracy has really become very relevant because we have politicians, not naming names, are just individuals in society who are happy to spread misinformation and misapply different areas of science. And because of that, I sort of wonder, what do you think is the role of professional scientists, or even sort of science outreach organizations like ourselves, BMUCO? What do you think is the role of people like us in trying to sort of combat this wave of misinformation regarding the science?
Well, I think it's very important. I mean, I agree with you. Science has been marginalized and used as a political tool. You know, the internet, which was supposed to be this great resource of human knowledge, it has become just a troll village of people misinforming each other all the time. And I like to think that that's a passing stage, that we will return to the days where an expert opinion would be trusted because that person knew the situation better and could see around the problem better. Because life is murky. The exact answers aren't usually known at this for a given question at this time. An expert opinion, I think, will play a role, not just in science, of course, in virtually any subject, you see it. And therefore, I think that institutions like this one that can support the voice of real experts, so we say, working in fields is important, because I hope that people can see that that's really where the valuable information is. I don't know what you can imagine a crackpot version of this. There are crackpot versions of conferences, and I think if you see them, and you'll see that nobody agrees with anybody, and they just walk away in a vacuum of noise. and so by getting people together, you can see the falsity of those ideas. Now, of course, politics makes everything a bit worse because people have very preconceived ideas, and they don't like them changed. But I think one has to have debates like this, so I appreciate what you do, actually.
Okay, well, I think we'll finish things off there. So thank you very much, Professor Lambert, for the brilliant talk and very informative Q&A. And I'll also say thank you to our collaborators, Physics Initiative Nepal, who are doing a lot of really amazing similar talks and seminars, programs. So definitely everyone in the chat, please check out Physics Initiative Nepal. And also we'd like to thank the QUB School of Maths and Physics, who are collaborating with us in this as well. So oh yeah, Professor Yang, I think he's here. So hi, Professor Yang. We'll be doing a talk with him within the next month or so. So yep, so if everyone who's here, just make sure you're signed up to our social media channels and sign up to Physics Initiative Nepal as well. And if you go there, you can just see all of our upcoming events, and we'll keep you informed of everything. So again, thank you, Professor Neil Lambert. Amazing talk. We're all very grateful that you took the time to give us this wonderful talk today. So thank you very much.
Thank you very much. I do appreciate it. Okay. Bye, everyone.